Welcome to today's Explainer. Come on into the garage, because today we are doing a deep dive, a real masterclass on building a race-winning engine head. We're going to break down the exact thermodynamics, the fluid dynamics, and the metallurgy I use to make an engine absolutely breathe fire and, more importantly, survive. Just think about this for a second. At 9,000 RPM, your valves are violently slamming open and closed 75 times every single second. 75. The mechanical violence happening inside that combustion chamber is just staggering. And if your valve train isn't perfectly engineered for that, well, the consequences aren't just a loss of power. We're talking about catastrophic, terminal engine failure. Boom. Done. Look closely at the engine valve here. This little piece of metal, it's the ultimate gatekeeper of your build. Honestly, any high-performance engine starts right here. You can throw on all the massive turbos, superchargers, or huge carburetors you want, but if you haven't maximized how the engine breathes through these precise mechanical gates, you're just leaving horsepower on the table. So let's jump right into phase 1, breathing for power. Now, the architectural leap from an old 2-valve design to a 4-valve per-cylinder head dramatically changes the game for airflow. 2 intake and 2 exhaust valves give you a significantly greater total valve area for the exact same cylinder bore. Plus, it lets you centralize the spark plug, which gives you a much more efficient combustion burn. It's a massive upgrade for high RPM breathing. This creates a continuous, violent cycle. You've got the intake valve constantly yanking in that cool, fresh air-filled charge, while the exhaust valve is tasked with shoving out the burnt gases. And keep in mind, that exhaust valve is operating in an absolute inferno. It's constantly exposed to exhaust gas temperatures that can easily, literally exceed 900 degrees Celsius. So how do we get more air past those gates to really maximize volumetric efficiency? Well, here's my exact formula as a builder. Step 1. Drop in oversized valves to increase the raw flow area. Step 2. Port and polish the metal around the valve seat to smooth out that airflow velocity. And step 3, the famous 3-angle valve job. We cut a precise 15-degree narrowing angle, a 45-degree seating cut for the seal itself, and a 75-degree throat cut. This perfectly transitions the air right into the cylinder and completely maximizes your peak power. 16 millimeters? Now that is an incredibly aggressive race cam valve lift spec. If we want serious top-end power, we literally have to shove those valves further off their seats. When you combine 16 millimeters of lift with a massive 280 to 320 degree duration, meaning the valve is forced to stay open much longer, we literally force the engine to take deep, massive breaths at high speeds. It completely changes your engine's performance profile. But, timing is everything. A completely crucial concept in performance engine building is valve overlap. This is that brief, tiny window when both the intake and exhaust valves are slightly open at the exact same time. By playing with camshaft timing, especially using variable valve timing systems to dynamically dial in this overlap, the exiting exhaust gases actually create a vacuum. This scavenging effect violently yanks the fresh air right in, drastically improving your high-speed performance. It's like a free supercharger.
All right, moving on to phase 2, surviving the red line.
Because let's be real, making power is the easy part. Making it survive the red line requires some aerospace-level metallurgy. Most good modern exhaust valves use austenitic stainless steel, which handles heat up to about 850 degrees Celsius. Great for the street, right? But if you're running a high-boost turbo build or extreme motorsports setup, stainless will literally melt like butter. For that, you need nickel-based superalloys, things like Inconel or Mnemonic, which maintain their structural strength well past 1,000 degrees Celsius. And if you're building the ultimate naturally aspirated track weapon, you look to titanium. Titanium valves drop your valve train mass by an incredible 40% compared to steel. Less weight means less valve train inertia, which is exactly how you hit those blistering, motorcycle-like RPM ceilings. The catch, though, titanium is kind of poor wear resistance, so it requires a specialized titanium nitride coating just to survive the constant friction. So why do we care so much about weight? Because of valve float. If your valve train is too heavy or your springs are just too weak, the valve literally fails to close fast enough to follow the backside of the cam profile at high RPMs. It just floats there, stuck open. And when the piston comes rushing up to top dead center while that valve is still hanging open, yeah, that's a terminal engine-destroying collision. Game over. To prevent valve float when we're running aggressive cams, we have to upgrade the springs. You've really got 2 main choices here. Dual valve springs, which is literally an inner spring nested inside an outer spring, provide the raw, heavy pressure needed to force that valve shut instantly. On the flip side, tapered beehive springs offer a much smaller, lighter top retainer. This drops the overall Valvetrain mass, giving you a beautiful balance of high RPM stability without needing the extreme, heavy pressures of a dual spring setup.
Which brings us to Phase 3, the pit stop. Let's talk diagnostics and maintenance.
Let's bring the engine back into the garage. I want you to think like a diagnostician for a second. Picture this. You're at the track, your engine starts misfiring, it feels completely flat, you're losing power, or maybe it's violently popping through the intake manifold. The fundamental question you have to ask is, where did your cylinder compression go? Well, here is your diagnostic Bible. Symptoms directly mapped to specific Valvetrain failures. If you've got a misfire from a burnt valve, you need to run a cylinder leak down test. If you see a puff of blue smoke on a cold startup, that points straight to worn guides or stem seals, which means doing a lateral movement test. And if your valve clearances just keep magically tightening up on you, you're dealing with seat recession. Let's break these down step by step.
The cylinder leak down test is absolute magic for diagnosing the stuff. You bring the piston up to top dead center, so both valves should be perfectly, completely closed. Then, you pump pressurized air into the spark plug hole. Now, you just listen. If you hear air hissing out of the intake manifold, your intake valve is sealing. If you hear hissing out of the tailpipe, your exhaust valve is burnt or stuck. Boom. You've instantly identified the exact cause of your compression loss.
Next up, if you're burning oil and suspect a worn valve guide, you do the lateral stem movement test. You take the spring off, open the valve just slightly, and physically rock the valve stem side to side with the dial indicator. If that lateral movement exceeds just 0.15 to 0.25 millimeters, actually, scratch that. If it hits that limit at all, your guide is completely trashed. It needs to be pressed out and replaced.
Now let's talk about valve seat recession. This is really common in older engines or heavy-duty applications. The maximum allowable wear here is incredibly tight, literally just 0.10 to 0.15 millimeters. If that valve sinks too deeply into the soft seat in the cylinder head, your mechanical valve lash hits zero. And when there is zero clearance, the valve never fully closes, the extreme combustion heat torches the edge of the valve, and it burns up entirely. Not good.
So to fix minor sealing issues or when you're doing a full rebuild, we do what's called valve lapping. It's a gritty, very hands-on process. You apply a fine abrasive lapping paste right to the valve face, drop it into the head, and physically spin and grind the valve against its seat. You are basically cutting a custom, perfectly mated surface between those two metals to ensure a vital gas-tight seal and get all your compression back.
But to prevent all of this headache in the first place, follow the builder's maintenance checklist. If you run mechanical tappets, you absolutely must check your valve lash clearances every 20,000 to 40,000 kilometers. Inspect those dual springs for fatigue. Check for hardened or cracked stem seals because, trust me, a $10 piece of hardened rubber can absolutely ruin a $10,000 engine block. Oh, and if you have a modern direct injection engine, constantly monitor for heavy carbon buildup on the back of the intake valves since there's no raw fuel washing over them to keep them clean.
Which brings us to our final thought. We've seen the extreme metallurgy required, the precision machining of a three-angle job, and the catastrophic failures that happen when just a single spring gets weak. Your engine might be breathing right now, but before you ever think about pushing that build to its absolute limit on the track, ask yourself, is your Valvetrain truly ready for the red line?